All right, team. Now I know we're on lecture 5. Ha ha ha. Okay, welcome back to lecture 5. Now that we went over generically how to release and then terminate neurotransmitter signaling, let's talk about some specific neurotransmitters, right? So what I want to show you folks, and do not memorize this spreadsheet, please. This is from a textbook, and I just rewrote it here. And some of these neurotransmitters we're going to get into great detail throughout the course. Not all right now, but slowly. But this is a trajectory. And some of these neurotransmitters, I'm not going to go into great detail. So don't memorize this slide. Just wait for us to move together as a unit throughout the lecture. Now, what I do want to do is I want to go over one neurotransmitter. And this is acetylcholine. And so acetylcholine is an important neurotransmitter because we need it to move. You want to go walk to the couch and turn on Netflix? Acetylcholine is involved. Also memory, right? So all this memory that we're trying to ingrain in our minds is all via acetylcholine. There's some other neurotransmitters involved, more on that later. And then if I have a ligand, acetylcholine, I have to have a receptor. And so acetylcholine has two receptor subtypes, and I will talk about those. And we're going to dive in. Let's start. So here we go. Here's our example acetylcholine. Look, number 1, I make acetylcholine. Do I care that you know it comes from acetyl-CoA and coenzyme A? No, I don't. Acetylcholine, know it, right? You can use the abbreviation big A, big C, small h, right? So here we go. Acetylcholine is made. Now, when we secrete acetylcholine into the synaptic cleft, of course, it's going to bind its receptor, and depending on what that receptor subtype is, it's going to facilitate some type of a cellular response. Now, if I want to turn off acetylcholine signaling, look, I have an enzyme, and this is a specific enzyme called acetylcholinesterase. Acetylcholinesterase, wave your wand. This is from Harry Potter. Acetylcholinesterase, right? And so you break down acetylcholine into parts, and then now it can no longer bind to the receptor. And guess what the body can do? It can take those parts, suck it back up into a reuptake channel, okay? Yes, it has co-transport with sodium, and that's another way that you can get sodium back into this presynaptic neuron, but don't worry about that. Reuptake channel, I get these parts back into the neuron, and I can make acetylcholine again. How beautiful is that? That I can recycle choline to make more acetylcholine. All right? So look what we did, people. We're layering our knowledge. I'm just repeating exactly what I did in the previous lecturette, except I'm putting name to faces now, right? I have neurotransmitter release. Acetylcholine was exocytosed into the synaptic cleft. It bound to its receptor. And then, of course, I have to have now neurotransmitter termination, and that is facilitated by acetylcholinesterase and then also these reuptake channels, and nothing has changed. Acetylcholine can also diffuse out of the synaptic cleft. All right, let's talk about acetylcholine receptor subtypes. Okay, now unit 1, right? Receptor subtypes. This is a clue because how many ligands do I have here? I have the 1. Okay, let's draw this out. Remember, this is our mantra, people. Ligand, or ligand for the chemists, plus receptor is gonna give us some type of a cellular response. All right, now, here we go. What's the ligand? Acetylcholine. Okay, this is all acetylcholine. There is one ligand. We have many receptors. Okay, so I'm going to draw them out here. And the first receptor that I'm going to write out is the name. And this is the I can't spell. There we go. Nicotinic receptor. And this causes depolarization. Okay? Now, acetylcholine can also bind to a receptor subtype called the muscarinic receptor subtype, of which there are two. Okay, so if I say muscarinic with a sub H here, this H stands for hyperpolarize. Okay, so I can have a hyperpolarization, but I can also have another muscarinic subtype. Muscarinic subtype, and this is what we're going to call M sub D. D, people. Guess what it does? Yep, it depolarizes. So I get depolarization. So here is a beautiful example where we have one ligand, and look, how many receptor subtypes does it have? 3. It has 3, leading to either depolarizing a cell that it binds to or hyperpolarizing a cell that it binds to. Okay, so let me talk about these receptors in more detail. And you got to memorize these receptors, people. We're going to be using this for the rest of the semester, these receptor subtypes. And these are your foundations. Okay, so here's this first one. Nicotinic. That's for acetylcholine receptor. Okay, so this nicotinic receptor is just a ligand-gated channel. Boom, boom, boom. And so when acetylcholine binds to it, right, that allows me to let sodium come traveling into the cell, and that leads to depolarization. So the nicotinic receptor is named after its ligand, nicotine. What you folks know about nicotine? Nicotine is the chemical found in cigarettes and tobacco, right? And so being that I used to smoke 1 to 2 packs of cigarettes a day, I would get the shakes. So if you're a cigarette smoker or no cigarette smokers, I mean, like really closely observe them, you'll notice like, oh my God, I need a cigarette to calm down. And then they'll smoke or chain smoke. But if you look at their hand, what's their hand doing? Shaking. You get the shakes. It's because you got so much nicotine binding to the skeletal muscle nicotinic receptors that you start having these mini contraction and relaxation events to where you shake. Okay, so nicotinic receptor, remember that it causes depolarization, and the depolarization in skeletal muscle, you're going to tell the skeletal muscle, hey, start contracting. Okay, so that's the nicotinic receptor. Now let me talk about the muscarinic receptor. So you folks notice that there's their family names, right? So this is the muscarinic acetylcholine. I'll just write it there because I don't want you folks to forget that this is where acetylcholine binds. Acetylcholine receptor. And they're 2 types, and it really depends on the cell's function. And we're going to get in great detail with muscarinic and nicotinic receptors when we talk about the autonomic nervous system. But for now, your foundations are the following. So my muscarinic receptor, if I am a cell type, right, that I need to turn off that cell, then the muscarinic receptor here is going to be now, if this is going to be for acetylcholine, if the muscarinic receptor causes me to have potassium leave the cell, what's going to happen inside of the cell? Am I going to depolarize or hyperpolarize? I'm going to hyperpolarize. And therefore, this muscarinic subtype, okay, is going to be what we call M sub H in our class, okay? H for hyperpolarize. Are you folks following me? So if I want to shut a cell off, turn it off, then I will stick a M sub H receptor subtype on it so acetylcholine can come turn that cell off. Now, if I want to turn a cell on, I'm going to have acetylcholine bind here. And if this is a ligand-gated channel to where I can have sodium come in, This is depolarize. Yes? Yes, because sodium is coming into the cell, more positive charge. This is going to be M sub D. D for oh my God. D for depolarize, right? All right. Those are your receptor subtypes that give you different cellular responses. Okay, memorize this, people. Know this like the back of your hand, or maybe you don't know the back of your hand that well. Know this like your name, your first name, okay? All right, let's move on. All right, so I'm going to go over a few examples of what happens when synaptic transmission is blocked, okay? Which means that I can't have any neurotransmitters or any ions then cross over through the synaptic cleft into the next neuron or effector, right? So, oh, blowfish. Okay, so this is people call this blowfish, people call this porcupine fish, and what I did was I got this little icon here, and it says sushi to die for, and this is because the pufferfish is a type of fish to where it has a very potent neurotoxin called tetrodotoxin. And this toxin is found in pufferfish, and it seems that in certain places this pufferfish is a delicacy because it's dangerous. It's dangerous because if you eat it, and if the fish cutter didn't cut the sushi correctly or the sashimi correctly, you could die. And it's all very fun and games until somebody actually dies. And I'm not gonna lie, when I was in my younger years as a professional dancer traveling across the world, I went to Japan and I did eat pufferfish, and I'm alive, so here I am. Let's go forward with tetrodotoxin. Now, it is a neurotoxin. It has absolutely no antidote. So if you eat this thing, you're done. Okay? And why are you done? You're done is because it will bind to sodium channels and it will block them, and there is no removing them. So far, what do you know? What is necessary for sodium? Why do we use sodium? We use it for every single neurotransmission in our central nervous system. If you block all those signals, you will die, right? Because you can't turn on your breathing muscles. You can't turn on anything. Your heart could beat by itself for a little while, but then you would terminate. Okay, so that's what this toxin does. It blocks sodium channels. You can't get sodium in cells or out of cells. You can't move sodium at all, right? And then that's why then it leads to loss of sensation or paralysis of voluntary muscles, right? Which can stop breathing. Interesting. Blowfish, do not eat it. Now, here's another thing that stops synaptic transmission, and this is this other toxin called botulinum toxin, aka Botox, right? And so this is extracted from this specific bacteria that we're not going to memorize the name because this ain't micro, but it's reversible with time. And what this Botox does is it inhibits the release of acetylcholine for muscles. Okay, so earlier I told you folks that acetylcholine can bind to its receptor, nicotinic receptor, and allow you to have muscle contraction. But this is what Botox does, and it's very popular in the media because you see people like, oh, I'm going to get my Botox shot and it's not going to allow my face muscles to move, and then all my wrinkles are going to disappear. But there is there's a medical reason as well. And for some people that get migraine headaches because of the uncontrollable contractions of some of the muscles around your head and neck, you can actually inject Botox in those muscles, decrease their contraction to minimize those type of migraine headaches. If you can get migraine headaches for different reasons. If the root of your migraines is because of muscle contractions or inappropriate muscle clenching, then Botox is for you and is actually covered with some insurance. So let me talk about the mechanism because, oh my God, Becky's, it is so amazing. Okay, now, do not memorize everything on this slide, okay? It's because I had to borrow without asking this slide from the web, and this is the best slide I could find. Now, let me show you folks what Botox is doing, because in teaching you about Botox, I can also teach you the mechanism of exocytosis. And I love this mechanism. So let's get started. Now, okay, let me slow down because otherwise I'm going to start talking really, really fast. Okay, now look, this is a synaptic vesicle carrying acetylcholine, okay? And this could be anything, carrying any protein. Now, in order to have exocytosis, I have to bring the vesicle down to the cell membrane, and the two vesicles need to touch, or sorry, not the two vesicles, but the vesicle needs to touch to the plasma membrane. And as soon as I get touching between the vesicle and the lipid membrane, the membranes will dissolve in each other. And then that's how I'll have exocytosis. All right, so we should all be in agreement. In order to have exocytosis, we have to have the two membranes, the membrane of the vesicle and the outermost portion of the membrane of the cell. They have to touch. How do we get them to touch? We get them to touch via snare proteins. So look at this slide. You see how there are 3 different snare proteins? I don't want you folks to memorize all the specific names of the proteins. Collectively, they are all snare proteins. We have a snare protein on a vesicle. Every vesicle will have one. And we also have snare proteins on our plasma membrane of the cell. Okay? Now, in order to have exocytosis, we need to have calcium. Okay? So what's going to happen here is calcium will bind to the snare proteins, causing them to change shape. When they change in their specific shape, you see what happens here? The calcium causes them to have a specific shape that allows them to hook together. So we hook, and then it also causes the protein to contract. So I contract these proteins, dragging. I drag this vesicle down until it touches the plasma membrane here, and then bam, exocytosis. That is the mechanism of exocytosis. Calcium binds to the snare proteins, causing them to change shape. The shape change causes the snare proteins to hook up on one another and drag the vesicle to the lipid bilayer, causing you to have exocytosis. Okay? Now, how does Botox stop acetylcholine release? Look what it does. Botox cleaves your snare proteins. It chops them off. You don't have them. That's what happens. But guess what? Your snare proteins will grow back in 3 months. Okay? So if you now get a Botox shot in your face and you don't like it, guess what? You're going to have to live with that. But don't worry, because in 3 months, your snare proteins will grow back, and then you'll have a regular motion of your face. Okay, now that's it for this lecturette. You come back. We're banging these out. This is a fun lecture, I hope. Well, it is for me. All right, bye.